pretty punny. You know what's cool to think about? Those reflections in the lake represent the light of stars, some of which have traveled thousands of years, over trillions of miles, before they arrive and finally hit the water. So what you're telling me is, light that's been traveling for thousands and thousands of years, over trillions and trillions of miles, can be stopped mere inches away from its final destination by simply reaching out my hand? Oh, you monster! Your shadow is confirmation. The light has traveled 93 million miles unobstructed, only to be deprived of reaching the ground in the last few feet, thanks to you. I think this very profound photograph here where you can look out and be seeing trillions of miles away, and looking at the geological structure you could be looking billions of years into the past. Very thought-provoking as you consider how old things are, how far away things are. Here is the star pattern of Orion. We've got the three kings, the Orion's belt, Sirius, the brightest star in the night sky. And we looked at the relative distances in terms of light years, recognizing these are trillions and trillions of miles away from us. And when you look at this flat image of the night sky, just flat, just the way it appears to us, if this set of stars were viewed from different angles, from greater distances from our solar system, we would definitely have different perceptions and different mythologies of what these stars might be representing in those newfound patterns. Here's the star pattern of Cygnus, the Swan, and the perception of looking out from planet Earth into the night sky. It appears as though it's flat, as though these dots, the stars, are all the same distance from us, but they most certainly are not. As you can see, Deneb here, over 1,500, or just about 1,500 light years away from us. Which, in terms of how many trillion miles away is that? Just a refresher, your 1,500 light years multiply by 6 trillion miles in 1 light year. So 6 times 0 is 0, 6 times 0 is 0, 6 times 5 is 30, 6 times 1 is 6 plus the 3, 9,000 trillion miles away is the star Deneb. The classic Big Dipper looks flat to our perception, what we see against the backdrop of our cosmos. And here, representing Earth, or it could even be our solar system, here is the relative distance that these stars are from Earth. So here are their distances in light years. And if you go back in your notes to page 8, this area right here where we have the asterism of the Big Dipper for you, we're going to have you jot down the names of the stars in the Big Dipper. The star names that are used are ones which honor the Arab contributions in continuing to propel the study of astronomy forward while the European nations were going through the Dark Ages. And so we'll start on the left and work our way around. So I'll start here, work our way around, and then back up. The star over here is known as Alkaid. The next star is like many stars that you gaze upon in the night sky. It's actually a double star system, and you can have triple, quadruple, quintuple, all along the lines there, multi-star systems. Mizar, and its binary star companion of Alcor. Alioth, Migras, Phecta, and then what we've been calling the pointer stars, we can actually give them individual names. We have Merak and Dubi. Here's a little challenge for you. This is an image that I'd like you to ponder. What is it that you're looking at? What's the perspective? And we'll have you press pause as you think about what this might represent. often guesses. People will say this is what the Big Dipper, recognizing many of the names of the stars there. So people might guess maybe this is the Big Dipper as it would appear from some other type of a system. That's not quite along the lines of what I was thinking in this challenge. It is a perspective of stars of the Big Dipper, except you'll notice one of the stars is not there. This is what the stars that make up what we on Earth call the Big Dipper, what the view of those stars would look like if being viewed from a star system with Alcade. So if you're maybe an Alcadian looking out into the night sky, this is how you would perceive what Earthlings called the Big Dipper. Other astronomy classes have dubbed it maybe the Great Shovel, Great Stick. Page 17, we have a little light astronomy for you. The purpose of this page is to go over 3 very common methods astronomers will use for measuring distances in space. We've mentioned what a light year is and an astronomical unit, but it's one thing to really think about, okay, how do you measure how far the sun is? It's not like you can take a measuring tape and say, okay, go deep, tell me how long the measurement is. We'll start here by looking at the first 2 methods on the page, not necessarily the first 2 methods used by astronomers, but the first 2 on the page, and we'll save the third one for another lesson. So you're going to identify the name and describe how these are able to determine measurements of stellar objects. So this first one we have here, this woman is Henrietta Swan Leavitt, so L-E-A-V-I-T-T. You want to get in your notebook, Leavitt. Henrietta Swan Leavitt. And what she came up with was realizing that a mathematical relationship that had been known since the beginning of mathematical computation by humans applied to light. And this mathematical relationship that applied to light is known as the inverse square law for light. I could go into a quick explanation for you of how your common sense tells you the farther away from a light source you are, the dimmer the light is because the area is spread over more. And you can actually calculate this value, that if you're, say, 2 units away, the light is dimmer by a factor of 1/4 because the area is spread over by 4 times. But I think the best way to describe the inverse relationship for you is with the butter gun example from a classic professor from, I believe it's the 1960s. You'll love it. The butter gun example.
The inverse square law is characteristic of anything that spreads out in straight lines without getting lost. I think I can illustrate that with a fable. Suppose a restaurant has the problem of buttering toast and wants to be very modern and do it with a machine. So the proprietor invents a butter gun with melted butter in here, which can be squirted out in straight line spray of butter like that. Here's the piece of toast, and lines of butter go out and hit it there, and there, and there, and there, and butter it all over. Now instead of that, lines might go on, and you could put the toast further back at twice the distance, 2 pieces of toast wide, 2 toasts high, and altogether you would put 4 pieces of toast there to intercept the butter, and you'd be half as thick, no, quarter as thick buttering. Inverse square law. At 3 times the distance, 3 pieces of toast, 3 pieces of toast, altogether 9 pieces of toast, and you would get 1/9 of the buttering economy treatment.
Fabulous. So you can get more coverage from a greater distance, but not as much butter. So more coverage meaning spread out over, but not more coverage in terms of thickness of the butter. In terms of the light example, much brighter at the beginning, or the butter example, you get all the butter in that wonderful click of the butter gun, whereas over here, the farther away from the light source you are, or from the butter gun, you'll get more coverage in terms of the light being spread out or the butter, but it's much dimmer. You don't have as much butter per piece as you would have close up here. So a quick look at the inverse square law for light. This is the piece of the moon that is in honor of Henrietta Swan Leavitt. So if we have a star that we recognize is perhaps a distance of, say, 5 times farther away from our sun, we would know that the light from that star is 1 over the distance squared. So 1 over the distance, whether it's 5 light years, 5 trillion miles, it's 5 squared, resulting in 1/25 as bright. So we kind of use the reverse of this. If we know the relative brightness of stars, maybe really bright versus dim, and maybe even dimmer, we can take and compare how bright these stars are compared to each other and say, okay, this star is 1/25 as bright as this star, so this has to be 25 times far, or 5 times farther away than the star that is 25 times brighter. So you take the brightness of stars compared to each other, and from that you can kind of work backwards and figure out how much farther the star is away. If this star were, say, 100 times brighter than this star, we would know that this star is 10 times further the distance away. So that's how the inverse square law for light helps us get measurements of how far away stars are from each other. Another method of measuring stars is this section right here we'll look at. Like I said, we'll save this for a later time. This method is where typically I'd have you hold up your thumb from a fully extended position, elbow locked, and you would put your thumb so it covered something against the farthest wall away from you. Oftentimes I'd have this projected on a screen, so maybe I'd say, okay, cover up the letter A with your thumb. And then what we would do is say, okay, without changing where your thumb's position is, we would have you open your left eye while you close your right eye and see the perspective that you see. And then we would have you simultaneously at the same time close your left eye and open your right eye and see how these letters would possibly appear to have moved, even though I guarantee you I wouldn't be pushing on the screen or the wall where the image is being projected. Since we're not in the luxury of a classroom here, here's what we're talking about. So we have this thumb, it's next to the stop sign, so I said, you know, to cover up something. This works equally as well. So you have your thumb next to something quite distinct in the distance, and then you would cover one eye, leave the other eye open. So if this were the right eye open and you haven't moved your thumb, the stop sign hadn't moved, you would see this perceived gap. Likewise, if you closed the right eye but opened the left eye, that gap is shorter. It's not that the thumb has moved, it's not that the stop sign has moved. This is a perception of change in distance. This is a very solid method of measuring how far away stars are from us. This method is known as parallax. So you want to jot that down in your notes, parallax. It's our second method on the page for measuring how far a star is. If you think about this as the top of your head, and this is your left eye, and this is your right eye, so you've got eyes on the very sides of your head. And let's say this star here is the star we want to know how far away from us is that star. So like we would be looking at this star with our thumb up and one eye closed and looking through our left eye only, we use these background stars. If this were, say, January, this is our perception. There's this star, and this one is in between the second and the third one. The star appears here. 6 months later, in July, now we close our left eye, open our right eye, and we look at this exact same star. Now it looks as though it's in the second rather than the third position. And it's not that that star has moved, we've moved relative to the star. And what we're able to then do is say, okay, we know that the average distance between the Earth and the Sun is 1 astronomical unit. This is our unknown distance. This is what we're trying to figure out. We can actually measure this angle. We've got a right triangle. Your wonderful trigonometry is going to allow you to find this distance. So parallax, a very well used and well tested method of determining how far stars are apart from one another and away from us. We'll leave you this image. It's a more pictorial representation of what we just showed you. This right here would be like your left eye. This is your right eye. This is the star in question, how it looks in January versus 6 months later. And then we're able to form these right triangles. So we could do it this way as well, knowing that that's 1 astronomical unit. We could calculate that distance because we would be able to determine the angle here.